Okay, let's just do a couple more practice problems of adding resistances because things are about to get a lot more complicated, so I want to make sure we can do these straightforward versions. Let's say we've got a 1.5 volt battery, and let's see, we've already done resistors in series and resistors in parallel, so let's mix things up a little bit. And suppose we've got a circuit that looks like this. We've got resistor 1, resistor 2, and resistor 3. And let's say they have resistances of 2 ohms, 3 ohms, and 4 ohms. How do we analyze a circuit like this? If we just start from the positive terminal and follow the current around the circuit, we go through resistor 1, and then the circuit splits here, and part of the current goes through resistor 2, and part of the current goes through resistor 3. So, and then everything comes back together, and there's no more resistors between here and the negative terminal of the battery. So the way we can think of this circuit is resistor 1 is in series with resistor 2 and resistor 3, which are in parallel. So we can analyze this circuit and find the total resistance of this circuit by finding the resistance of this. We'll call this RP, and adding that resistance in series with resistor 1. So what would the resistance be of R2 and R3 in parallel? Well, we know that 1 over that resistance is going to be equal to 1 over R2 plus 1 over R3, which is 1 over, what was that? R2 is 3 ohms, that's confusing. R2 is 3 ohms, and R3 is 4 ohms. And that's, remember, this is 1 over RP. So 1 over RP is a third plus a fourth. 3 inverse plus 4 inverse equals 0.58333. And RP is 1 over that, which is 1.71 ohms. So the resistance of these two resistors in parallel with one another is the same as if the circuit, and I'll redraw it just to be really explicit here. If R1 was just in series with RP equal to 1.71 ohms. Okay, so we can fold together these two parallel resistors into a single resistor that effectively has a resistance of 1.71 ohms, and then so the total resistance is just going to be equal to R1 plus RP, which is 2 ohms plus 1.71 ohms, which is equal to 3.71 ohms. Okay, so as we get to more and more complicated circuits, we can break them up into parts and find the resistances of the different parts of the circuit one at a time. If we wanted to know the current through the circuit as a whole, we could just use Ohm's law, V equals IR. So I is equal to V over R, which is equal to 1.5 volts divided by 3.71 ohms, which is equal to 1.5 divided by 3.71 is 0.404. We'll just round that to 0.4 watt. Current is in amps. An ohm is a volt per amp, so volts over ohms is amps. What does that current mean if we find the current through the whole circuit? That is the current through this part of the loop and through this part of the loop, okay, it is not the current through these individual branches of the loop where the current splits. At this point in the circuit, the current splits, and some of the electrons will go this way and some of the electrons will go this way. And there's no way to know what fraction of the current goes through these two branches without doing something a lot more complicated, which is what we'll be doing in the next course. When everything comes back together again, you've only got one current in one branch, and the current here is equal to 0.4 amps. So when you're finding the current through the whole circuit, you're finding it through the parts of the circuit where nothing is branched. To find the current through the branched part of the circuits is quite a bit more complicated. Let's do another example. Let's have a circuit that looks like this. We'll put the battery up here this time. We'll make it a 9-volt battery. And we'll have something like this. Okay, so we've got 5 resistors. We'll label them R1, R2, R3, R4, and R5. And let's make them, we'll give them some values. R1 equals 4 kiloohms. R2 equals 6 kiloohms. I'm just pulling these numbers out of thin air. R3 equals 1 kiloohm. R4 equals 7 kiloohms. And R5 equals 9 kiloohms. Okay. So what is the resistance of this total circuit, and what is the current through the parts of the circuit that are not branched? So if we look at this circuit, what we've got is, we can think of this as 3 separate sections. We've got R1 and R2 in parallel with one another. We've got R4 and R5 in parallel with one another. And this part of the circuit and R3 and that part of the circuit are all in series with one another. So we can decompose the circuit into an effective resistance of 1 and 2 and an effective resistance of 4 and 5. Let's just call that R12 and R45 and R3. And then the total resistance will be the sum of, R total will be equal to the sum of R12 plus R3 plus R45. So all we need to do is find the resistance of these 2 blocks and add them all up in series. So let's find R12. R12 is going to be equal to, R1 is 4 kiloohms plus R2 is 6 kiloohms, 1 over that, right? Using the rule for adding resistors in parallel. So let's do that. 4 inverse plus 6 inverse equals 0.41666 inverse equals 2.4 ohms. Kiloohms, sorry. 2.4 kiloohms. Notice that the resistance of the 4 kiloohm resistor and the 6 kiloohm resistor in parallel with one another is less than either of their individual resistances. R45 will be the sum of these 2 resistors, 4 and 5, in parallel with one another. So 1 over 7 kiloohms plus 1 over 9 kiloohms, inverse 1 over that. 7 inverse plus 9 inverse equals 0.25-ish. 1 over that is 3.9, 3.9375. Go ahead and round that off to 3.9. Okay. And we can now think of the whole circuit as being this combination of resistors with a resistance of 2.4 kiloohms, plus resistance of resistor 3, which is just 1 kilo ohm, plus the combination of resistors that constitute this little parallel bit of the circuit, 3.9 kilo ohms. And that total resistance is just the sum of those, which is 2.4 plus 1 plus 3.9, which is 7.3 kilo ohms. If we wanted the current through the non-split parts of the circuit, we would use Ohm's law of E equals IR, so I equals V over R, which is 9 volts divided by 7.3 kilo ohms. Watch your units here. That would be 9 divided by 7300 ohms, which is 1.2 times 10 to the negative 3, or 1.23 milliamps of current. Okay, so 1.23 milliamps is the current through this part of the circuit, and this part of the circuit, and this part of the circuit where the current is not split. Here where it splits between resistor 4 and 5, here where it splits between resistor 1 and 2, we have to do something quite a bit more involved to figure out how much of the current goes through each of those branches. Let's do one more. What have we not done yet? We haven't done something like this yet. Let's put our battery down here. Make it a 12 volt DC battery. Let's put a resistor here, R1. Why not? Do one more. Okay. So R1, R2, R3, R4, R5, R6, and R7. So we've got 7 resistors in our circuit. Let's give them some resistances. Let's say R1 is equal to 10 ohms, and R2 through 5 are equal to, I don't know, 2 ohms. And R6 is equal to 3 ohms. And R7 is equal to 4 ohms. So what have we got? We've got from the battery, from the positive terminal of the battery, we've got one resistor that is then in parallel with this whole chunk of resistors. And that's in series with this and this. Let's call this Rx. So we've got, if we simplify our circuit, we've got our 12 volt battery, we've got R1, Rx, R6, and R7, which are all in series with one another. So the total resistance of the circuit is R1 plus Rx plus R6 plus R7. And all we have to do is figure out the resistance of Rx. What is Rx? Rx is a parallel piece of the circuit. The current splits here and goes 2 ways. So this and this are in parallel with one another. And inside each branch of this parallel circuit, there are 2 resistors in series. So the first thing we can do is rewrite this as being equivalent to, these 2 resistors are in series with one another. They all have a resistance of 2 ohms. I did this just to make it simple. R2, 3, 4, and 5 all have resistance of 2 ohms. So this is like a 4 ohm resistor, R2 plus R1, sorry, R2 plus R4, and a 4 ohm resistor, R3 and R5, right? Because each has a resistance of 2 ohms. So 2 plus 2 on this side, 2 plus 2 on that side. So the resistance of this, Rx, is going to be equal to 1 over 4 ohms plus 1 over 4 ohms inverse. Right? 1 over Rx is 1 over 4 plus 1 over 4. 1 over 4 plus 1 over 4 is 2/4, which is a half. 1 over that is 2. So the resistance of that whole bunch of resistors together is 2 ohms, which means the resistance of the total circuit is R1, which is 10 ohms, plus Rx, which is 2 ohms, plus R6, which is 3 ohms, plus R7, which is 4 ohms. And that is, what, 2 and 3 is 5, that's 19 ohms, is the resistance of that whole circuit. If we wanted the current through this part of the loop, not counting the little parallel part, the current through that part of the loop where the current is all going through the same wire, is going to be V over R, which is 12 volts over 19 ohms. 12 divided by 19 is 0.63 amps of current. Okay, so I'll probably give you a lot of practice problems like this. I actually find them kind of fun, weirdly enough, going through the process of breaking down the circuit into its smaller and smaller components. And you can make these as crazy as you want. You can have a parallel circuit with 3 branches, each of which has resistors in series with one another. You can have that in series with 2 other resistors. Okay, so to approach this, you would find the resistance of these in series, then you add these in parallel, then you add those in series with these 2. So I'll give you some more example problems like that. We'll do a bunch of these, and then we'll be ready to move on to the question of how do you, when you are faced with a circuit where the current splits through these various branches, how do you figure the current through each of these branches? To do that, we have to apply something called Kirchhoff's laws, and it's really, to be honest, quite unpleasant. It's one of those things that I really don't like teaching that much. Remember back in first semester when we talked about collisions? You've got M1, M2, V1, V2, and you want to find out their final velocities. We almost always did it by specifying the final velocity of one of these, because if not, you have to apply conservation of momentum. M2, V2 equals M1, V1 final plus M2, V2 final. And you have to apply conservation of kinetic energy. So 1/2 M1, V1 squared plus 1/2 M2 V2 squared equals 1/2 M1 V1 final squared plus blah, 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 blah. And you apply these things together and you get a giant quadratic that is terrible to solve. And I only did it once just to show that we can do it. And I never really made you do one of these problems yourself, where you have to apply both conservation of momentum and conservation of energy, because the problem gets really ugly and there's a lot of places to make algebraic mistakes. The thing we're going to do next, which is called Kirchhoff's laws, is sometimes Kirchhoff's rules, sometimes laws, depending on your textbook, is the same kind of thing. It is a somewhat cumbersome project where there's lots of places to make mistakes. So we'll do a few of those. I'm not sure. Maybe I'll make you do 1 or 2 for homework. Kirchhoff's rules problems are not the kind of things I will ever put in an exam, just because they are incredibly unpleasant types of problems to solve. But we got to do them, so we'll do. I'll probably record some lectures on that tomorrow, and then we'll look at that on Thursday, and then we'll move on to the next thing.